Lesson 5, Optimal Portfolios. By the end of this lesson, you should be able to calculate the portfolio return and standard deviation for a multiple asset portfolio, discuss mean variance, optimization, and efficient portfolios, and explain systematic, unsystematic risk, portfolio risk, and beta. In the last lesson, you learned that the standard deviation of a two-asset portfolio is the square root of the following summation. The squared weight of asset A times the variance of asset A plus the squared weight of asset B times the variance of asset B plus 2 times the weight of A times the weight of B times the covariance of AB. Notice that the first and second terms in this summation are simply the squared weights of each asset's variance. The third term is what accounts for how the assets move relative to one another. This term is 2 times the weight of asset A times the weight of asset B times the covariance of AB. Another way to express this formula is the squared weight of asset A times the covariance of asset A with itself plus the squared weight of asset B times the covariance of asset B with itself plus 2 times the weight of asset A times the weight of asset B times the covariance of assets A to asset B. As a formula, you can express the standard deviation of the portfolio as the square root of the weight of asset A times the weight of asset A times the covariance of asset A with asset A plus the weight of asset B times the weight of asset B times the covariance of asset B with asset B plus 2 times the weight of asset A, weight of asset B times the covariance of AB. It may not look like it at first glance. However, the two equations on this slide are the same. Let's focus on the second formula. The weight of asset A times the weight of asset A is the same as the weight of asset A squared. The covariance between a security and itself is the asset's variance. Why is that true? Remember that covariance equals the correlation coefficient times the standard deviation of the first asset times the standard deviation of the second asset. In this case, the movement of asset A is compared to itself. That means that the correlation coefficient is 1. So, 1 times the standard deviation of asset A times the standard deviation of asset A equals asset A squared standard deviation, or variance. The same procedure is used to calculate the second term in the equation, the squared weight of asset B times the variance of asset B. Where does the third term come from? To understand that, let's look at the covariance matrix. The standard deviation of a portfolio reflects the weighted risk of each portfolio holding and the way each asset moves relative to every other asset in the portfolio. The covariance matrix helps you visualize what this means. The first matrix shows 2 assets in a portfolio. The covariance reflects how weighted asset A moves relative to itself and to weighted asset B. It also reflects how weighted asset B moves relative to weighted asset A and to itself. As you see, there are 4 components to consider when assessing how the movement of each asset versus the other asset affects portfolio risk. The same logic applies to a 3-asset portfolio. You multiply each of the covariances in the matrix by the portfolio weights. Therefore, there are 9 components to consider when assessing the risk of a 3-asset portfolio. Let's examine the 2 and 3-asset covariance matrices. Look at the 2-asset covariance matrix on this slide. The 2 assets are A and B. As you see, you must consider the weighting of each asset in the portfolio and how each asset moves relative to every other asset in the portfolio. In this example, you must consider how weighted asset A moves relative to weighted asset A and to weighted asset B. You must also consider how weighted asset B moves relative to weighted asset A and to weighted asset B. This gives you four relationships. The weight of asset A times the weight of asset A times the covariance of A to A plus the weight of asset A times the weight of asset B times the covariance of AB plus the weight of asset B times the weight of asset A times the covariance of BA plus the weight of asset B times the weight of asset B times the covariance of BB. Simplifying this, you can get the standard deviation of the portfolio as the square root of the squared weight of asset A times the variance of asset A plus the squared weight of asset B times the variance of asset B plus 2 times the weight of A, weight of B, covariance of AB. You already studied this equation in the last lesson. Now, look at the three asset covariance matrix on this slide. The three assets are A, B, and C. Again, you must consider the weighting of each asset in the portfolio, and you must consider how each asset moves relative to every other asset in the portfolio. When you do this, you discover 9 relationships. The weight of asset A times the weight of asset A times the covariance of A to A. The weight of asset A times the weight of asset B times the covariance of AB. The weight of asset A times the weight of asset C times the covariance of AC. The weight of asset B times the weight of asset A times the covariance of BA. The weight of asset B times the weight of asset B times the covariance of B to B. Weight of asset B times the weight of asset C times the covariance of BC. The weight of asset C times the weight of asset A times the covariance of CA. The weight of asset C times the weight of asset B times the covariance of C to B. And finally, the weight of asset C times the weight of asset C times the covariance of CC. Simplifying this, you get the standard deviation of the portfolio as the square root of the following sum. The squared weight of asset A times the covariance of A to A, the squared weight of asset B times the covariance of B to B, plus the squared weight of asset C times the covariance of C to C, plus 2 times the weight of A times the weight of B times the covariance of AB, plus 2 times the weight of A times the weight of C times the covariance of AC, plus 2 times the weight of B times the weight of C times the covariance of BC. Let's work an example for a 3-asset portfolio. This risky portfolio consists of 3 assets: a large cap stock, a long-term government bond, and a small cap stock. The large cap stock accounts for 30% of the total portfolio. The bond and small cap stock account for 40% and 30% respectively. In this example, you're given the following expected returns, standard deviations, and correlation coefficients. The large cap stock has an expected return of 12.5% and a standard deviation of 20.4%. The long-term government bond has an expected return of 6% and a standard deviation of 8.7%. The small cap stock has an expected return of 17.7% and a standard deviation of 34.4%. The correlation coefficient between the large cap and small cap stocks is 0.81. The correlation coefficient between the large cap stock and long-term government bond is 0.22. And the correlation coefficient between the small cap stock and the long-term government bond is minus 0.01. As you learned in the last lesson, the expected return of a portfolio is going to reflect to some degree the return of each asset. The amount that each asset contributes to the total return is a function of its weight within the portfolio. In this example, the large cap stock has an expected return of 12.5. Its weight in the portfolio is 30%. Therefore, its contribution to the total expected return of the portfolio is 3.75%. Calculating the weighted return of the small cap stock and long-term government bond, you find 5.31% and 2.40% respectively. Adding up the weighted returns gives you an expected portfolio return of 11.46%. Given the standard deviation of the three assets, the correlation coefficients, and the weights of the assets, you can solve for the standard deviation of the portfolio. On this chart, you see the three asset covariance matrix and the resulting formula for the standard deviation of the three asset portfolio. The first term is the squared weight of asset A times the covariance of asset A. That is equal to 0.3 squared times 0.204 squared. The next two terms are the squared weight of asset B times the variance of asset B, and the squared weight of asset C times the covariance of asset C. The last three terms are 2 times the weight of the first asset times the weight of the second asset times the covariance of the two terms. Covariance equals the standard deviation of the first asset times the standard deviation of the second asset times the correlation coefficient. Let's continue to look at these calculations on the next chart. You know that the covariance of two assets is equal to the standard deviation of the first asset times the standard deviation of the second asset times the correlation coefficient of two assets. The correlation coefficient, describing the relationship between the large cap stock and the small cap stock, is given as 0.81. The standard deviation of the large cap stock is 20.4. The standard deviation of the small cap stock is 34.4%. Inputting this data into the formula for covariance, i.e. covariance coefficient rho times standard deviation of A times standard deviation of B, gives you 5.68%. When you multiply that number by 2 times the weight of A, i.e. 30%, times the weight of B, i.e. 30%, you get 1.02. The same procedure is used to discover the value of the last two terms, 0.09% and minus 0.07%. Adding up the 6 values, you find that the portfolio's variance is 2.60%. Taking the square root of that number, you discover that the standard deviation for this 3-asset portfolio is 16.14%. You know that the standard deviation of a 2-asset portfolio can be calculated with the formula shown. Now, let's analyze the effect of combining assets with different correlation coefficients, i.e. diversification. What happens when the correlation coefficient is +1? What happens when there is no correlation? And what happens when two assets have a correlation coefficient of -1? When the two assets exhibit perfect positive correlation, i.e. rho equals +1, there is no risk reduction due to offsetting price movements. In this situation, the standard deviation of the portfolio, sigma p, is just the weighted average of the individual standard deviations. The weight of asset A times the standard deviation of asset A plus the weight of asset B times the standard deviation of asset B. When there is zero correlation, i.e. the covariance rho equals 0, sigma p is simply the square root of squared weight of asset A times the variance of asset A plus the squared weight of asset B times the variance of asset B. This is because the third term, 2 times the weight of A, weight of B, covariance, equals 0. When the two assets exhibit perfect negative correlation, i.e. -1, there is maximum risk reduction due to offsetting price movements. In this situation, sigma p, or the standard deviation of the portfolio, is just the absolute value of the weighted difference of the individual standard deviations. The weight of A times the standard deviation of asset A minus the weight of B times the standard deviation of asset B. Let's verify the correlation summary from the last slide by calculating portfolio standard deviations. Look at the table on this slide. The standard deviation of the portfolios A and B have been calculated for varying correlation coefficients. As you would expect, the portfolio standard deviation drops as you combine assets that are less positively correlated. Consider portfolio A, which is weighted 50-50 between assets A and B. In A1, the correlation coefficient is +1. When assets are perfectly correlated, the portfolio does not benefit from offsetting movements of return. Therefore, the standard deviation of the portfolio is simply the weighted average of the assets' individual standard deviations. In this case, the portfolio standard deviation is 8%. In A2, the correlation coefficient is +0.5. Although there is still a positive correlation, the portfolio does benefit from the combination, and as you see, the standard deviation of the portfolio drops to 7. In A3, there is 0 correlation. That means that the standard deviation of the portfolio is the square root of the sum of each asset's squared weight times the variance. The standard deviation of the portfolio drops to 5.83%. Portfolios A4 and A5 have negative correlations, and as you would expect, the risk of the portfolio drops even further. Portfolio B is weighted 90-10 between assets A and B. As expected, the portfolio standard deviation drops as the correlation coefficient between the two assets move from perfectly positive correlation to perfectly negative correlation. However, because the portfolio weighting in the one asset is 90%, the positive effect of diversification is muted relative to the 50-50 portfolio. Let's continue with this study of how correlation coefficients affect the risk of a portfolio by considering the following question. What would the two asset portfolio's expected return and standard deviation look like holding the following data constant while changing the correlation coefficients from +1 to +0.5 to 0 to -0.5 to -1? The graphic on this chart depicts the different risk-return opportunity sets. Notice that the perfectly correlated two-asset portfolio has the worst risk-return profile. The investor must assume a higher level of risk for a given level of return as compared to any of the other diversified portfolios. Also notice that the best risk-return profile is the portfolio with perfect negative correlation. This portfolio offers the highest level of return for a corresponding level of risk. This graphic summarizes the importance of diversification. Adding assets that are not perfectly correlated help reduce the level of risk for a given level of return. Expected return and correlation matrix calculations for portfolio standard deviation can be calculated for all the different combination sets of asset allocation. Once all the mean variance combinations are calculated, minimization techniques can identify that allocation combination that produces the lowest level of risk for any given level of expected return. Before continuing on, let's review the topic of mean variance that was first introduced in Lesson 2. Modern portfolio theory confirms that rebalanced, diversified portfolios investing in assets that are liquid can be described by normal distributions. That suggests that the mean, i.e. the expected return, and the square dispersion of returns around the mean, i.e. variance or standard deviation, are sufficient to describe the distribution. Are there other ways of describing distributions? Yes. Distributions can be examined in terms of asymmetric of the distribution around the mean and the peakness or flatness as compared to a normal curve. Let's examine the concept of central tendency in a little more detail. Central tendency is a statistical measure to describe the distribution with a single number that is most representative. For example, mean, weighted mean, median, mode. While the expected return, referred to as the first moment, is a useful measure of central tendency, the shape of the distribution can be important for investment analysis. Three measures of distributional shapes are variance, which is the second moment, skewness, which is the third moment, and peakness or flatness, which is the fourth moment. Knowing that the mean and the variance are sufficient to describe the risk-return profile of an asset within a diversified, rebalanced portfolio provides the foundation for portfolio optimization. Mean variance optimization is the process of identifying optimal portfolios of risky assets, e.g. stocks, bonds, commodities, etc. In other words, computers can be used to quickly calculate the overall portfolio, expected return, and standard deviation for different combinations of assets. Once that is done, the portfolio offering the best expected return for a given level of expected risk can be identified. These optimal portfolios lie along the efficient frontier. The efficient frontier depicts the minimum variance portfolios for the data set of expected returns, standard deviations, and correlations. That means any portfolio lying on the efficient frontier has the optimal return to variability payoff, i.e. the minimum risk for a given level of return. An efficient frontier can be generated for any set of assets and constraints. For example, eliminating certain asset categories, etc. Take a look at the graphic on this slide. The x-axis depicts the given level of risk as measured by portfolio standard deviation, and the y-axis depicts the portfolio's expected return. The entire opportunity set of all the different asset allocations is graphed. They appear as the green diamonds. Once the risk-return profile of the entire opportunity set is known, the efficient frontier can be determined. As just explained, the efficient frontier describes the optimal risky asset allocation for each level of risk. The actual portfolio chosen for an investor would reflect the given level of risk the person is willing to hold. Notice that all portfolio allocations below the efficient frontier are obtainable, but inefficient. They are inefficient because there is another allocation that offers a higher return for the same level of risk. Look at the graphic on this slide. Do you see what happens when an investor's portfolio consists of a risky asset plus a risk-free asset? The investor achieves a higher risk-return profile by holding a combination of risk-free asset and the risky asset in every case but one. That one case is the point of tangency between the capital asset line and the efficient frontier. The combination of the risky asset and the risk-free asset offers the investor a wide range of risk profiles to choose from. By adding the risk-free asset, there is a new range of portfolios with lower risk than originally available with only the risky asset. The conservative investor can weight the portfolio with risk-free assets, i.e. U.S. T-bills, and maintain portfolio risk below any available by holding just the risky asset. The aggressive investor might borrow money at the risk-free rate and invest it in the risky asset. That risk-return profile is described on this graphic as the CAL extending beyond the point of tangency and continuing upward and to the right. Let's summarize the last two slides. The efficient frontier describes the optimal risky asset portfolio. Once a risk-free asset is introduced, the investor can achieve a higher risk-return profile by holding a combination of risk-free and risky assets in every case but one, and that one case is the point of tangency between the capital allocation line and the efficient frontier. When a risk-free asset is added, there is only one risky asset portfolio mix for everyone. That risky asset mix is defined by the point of tangency, i.e. the intersection of the capital asset line and the efficient frontier. The only choice the investor needs to make concerns the percentage of assets to put into the risky portfolio and the percentage to put into the risk-free asset, i.e. the asset allocation decision. So how might an investor make the asset allocation decision concerning the best percentage of assets to put into the risky asset and into the risk-free asset? That can be done with either the utility function or the indifference curve. You learned about these two concepts in the last lesson. The allocation of total assets to the risky asset can be calculated by dividing the excess return by the utility function. You could also plot the investor's indifference curve and then find a point at which the curve is tangent to the CAL line. Let's first work a problem using the utility function. In this example, the point of tangency between the capital asset line and the efficient frontier is the risky portfolio that has an expected return of 17.7% and a standard deviation of 34.4%. That is the risky portfolio for everyone. The risk-free rate is given as 6%. The utility function is the excess return, the expected return of the portfolio minus the risk-free rate, divided by the utility function, 0.01 times A times the variance of the portfolio. This is used to determine the allocation to the risky asset. Let's consider the more conservative investor first. The aversion index for this person is 4. Remember, since the aversion index is in the denominator of the equation, a higher number will result in a lower allocation to the risky portfolio. Inputting the data, you find that 17.7% minus 6% equals 11.7%. That is the numerator of the equation. The denominator is 0.01 times 4 times 34.4 squared, or 0.4733%. Working the solution, you discover that the allocation to the risky portfolio for this conservative investor is 24.7%. That means that the allocation to the risk-free asset is 75.3%. Using the same methodology to calculate the allocations for the intermediate and assertive investor, you will discover allocations to the risky asset of 33% and 49.4% respectively. The graphic on this slide depicts the efficient frontier, the risk-free rate, and the capital asset line. The investor's indifference curve is also shown. As you will see, the intersection point of the indifference curve and the investment opportunity set, as described by the CAL, shows the expected return and standard deviation of the optimal allocation. Based on those numbers, the allocation to the risky portfolio could be solved. Practical application question. How do professionals in the financial planning community allocate an investor's assets? Answer. CFP and other professional financial planners ascertain the investor's risk profile, for example, conservative, moderate, aggressive, determine the client's investment time horizon, for example, short, intermediate, or long term, and then allocate assets according to mean variance optimization. In making client presentations, the CFP and other professional planners might use a pie chart graphic, similar to the one on this slide, to help the client visualize what an appropriate asset allocation for them looks like. Consider this chart for a moment. In this example, the investor has been identified as long-term aggressive with a long-term investment horizon. The investment assets of that individual might then be allocated according to the following distribution. The planning professional might also use an allocation matrix rather than a pie chart. There is an excellent article entitled Assessing Risk Tolerance for Asset Allocation by William Drones and Stephen Strauss at the following Journal of Financial Planning website. Exhibit 4 in this article shows an allocation matrix that was most likely produced using mean variance optimization. Financial securities are subject to two broad categories of risk: systematic, i.e. market risk, and unsystematic, i.e. firm-specific risk. The first category explains risk in terms of the macro perspective. The second addresses risk from a micro perspective. Examples of systematic or market risk are stock market risk, interest rate risk, currency exchange risk, inflationary or purchasing power risk, and reinvestment rate risk. Unsystematic or firm-specific risk include business risks associated with the individual company, for example, loss of market share, poor management decisions, profit margin erosion, etc. Financial risks associated with the individual company, for example, credit rating downgrades, default on fixed obligations, liquidity risk, etc. Modern portfolio theory supports the argument for diversification. Prudent diversification eliminates unsystematic risk, leaving only systematic or market risk. That has practical, profitable implications for the investor. Holding somewhere between 15 and 20 large-cap stocks in different sectors and industries eliminates unsystematic risk. Theory suggests that 25 to 30 stocks are needed if they are small-cap firms. Note that market risk cannot be diversified away. When market uncertainty, higher inflation, or shocks to the system occur, nearly all financial securities will be adversely affected. Diversification may mute the overall effect some. However, the portfolio will not be insulated. To summarize, total portfolio risk equals market or systematic risk plus company or unsystematic risk. Question. You now know that effective diversification eliminates the unsystematic risk. What implication does diversification have on measuring total portfolio risk? Answer. Standard deviation is no longer the relevant risk measure. Rather, the amount of systematic risk as measured by beta is the relevant measure for diversified portfolios. Beta is a measure of the systematic risk associated with a specific asset. It is a relative index measure of security price volatility as compared to that of a corresponding market. Since the market's beta is 1 by definition, a company with a beta less than 1 has less volatility than the market. A company with a beta greater than 1 has more volatility than the market. Beta can be calculated with the following formulas. Beta equals the covariance of A to M divided by the variance of the market. Knowing that covariance of A to M equals the standard deviation of A times the standard deviation of the market times the correlation coefficient of A to M, you can simplify the formula for beta to be standard deviation of A divided by the standard deviation of M times the correlation coefficient of A to M. Beta can also be calculated by linear regression. Notice on this graph that the return of the stock is plotted along the y-axis and the return of the market is plotted on the x-axis. Once all the points are plotted, the regression line can be calculated. Beta is described by the slope of the regression line. So now, when adding a security to a diversified portfolio, you aren't concerned with the total risk of the asset, but only with the amount of systematic risk the asset will contribute to the portfolio. The beta of an entire portfolio is simply the sum of the weighted asset betas. Let's work an example. Question: what is the beta of a portfolio given the following portfolio weightings and security betas? The beta of this portfolio is equal to 30% times asset A's beta of 1.7 plus 50% times asset B's beta of 1.2 plus 20% times asset C's beta of 0.8. The beta of the portfolio is 1.27. Remember, a portfolio with a beta less than 1 means the security fluctuates less than the corresponding market index. A beta greater than 1 indicates greater volatility. In this lesson, you learned about portfolio return and standard deviation for multiple asset portfolio, mean variance optimization and efficient frontiers, and systematic risks, unsystematic risks, portfolio risk, and beta.